So given the abstract representation of a tensor in the form of a fiber tree that we just discussed, I'm going to talk now a little bit about what are the concrete implementation choices that we can make for actually implementing a tensor. And so first we want to look at what was the information in that fiber tree representation. And the way to think about it is that each fiber has a set of coordinate payload tuples. And so if we look at an element of the bottom rank and a fiber within that rank, inside the fiber are coordinates, and each of those coordinates has a payload. In this case, because we're in the bottom rank, and it's a fiber in the bottom rank, the payload is a value. However, we also have coordinates at higher ranks, and those higher ranks also have a payload, and the payload is a reference to the next rank. Now, in order to make this transition from this abstract representation into a concrete representation, we're going to focus on the choices for the representation of a fiber. And so here's a couple of examples of fiber representations, the actual contents of memory for representing a fiber. One is just include the elements of the fiber in an array, be they 0 or not. And so what we have here is an array. Each of the elements of the array is a payload. And in order to find something, we know that each of these values along the way is its coordinate. And in fact, the interesting aspect of this representation is that each coordinate also corresponds to its location or position in the array. And so in that case, it's very easy to find a coordinate by just accessing the data at a particular position in the array. An alternate representation of a fiber could be something you might call a coordinate payload list. And here we actually have a list of coordinates and a list of payloads. If we reference things in this structure by position, what we will get are the non-zero coordinates. So we would just go through them sequentially. However, if we want to find a particular coordinate, we're going to have to look up in this structure and find where, say, coordinate 5 is, and then find out that its payload is F. So we actually have a lot of choices for how we might want to represent fibers. Some of the attributes of those choices are the coordinates implicit in the representation? In that array representation before, which you might call an uncompressed representation, we never had to explicitly specify the coordinates, so there was no metadata required. However, there's another representation where the coordinates are implicit, which would be compressed, for example, by using a run length encoding. So both of those are examples of representations where you don't actually see the coordinates in the data. On the other hand, you can have representations where the coordinates are explicit, like in the coordinate payload list that we described before. Another choice you have is the data compressed or uncompressed? In this case, I'm using compressed or uncompressed as an attribute of the representation, where uncompressed means that the size is proportional to the maximum coordinate value. On the other hand, compressed formats will have metadata overhead relative to uncompressed formats. However, for dense data, this may cost more than just using an uncompressed representation. Therefore, what you'll see is that the space efficiency of a representation is going to depend on sparsity. Now, a nomenclature or terminology convention that I'm going to try and use here is that, as I said before, compressed or uncompressed is an attribute of the representation. I'm going to try to use the terms sparsity or density of a tensor as an attribute of the data. So I'm not going to talk about dense formats. I'm going to try and use the word dense to refer to the statistical properties of the tensor or a fiber of the tensor. So a few examples here. A compressed implicit coordinate representation. As I said, I could have empty coordinate compression via zero run length encoding. So that could be either using standard run length encoding, where you have every element of the fiber being a tuple. One piece of that tuple is the run length of zeros preceding this non-zero payload, and then you put the payload into the second element of the tuple. Or you might use something that's referred to as significance map coding. And here you also have a tuple, which each element has a flag to indicate if the element is zero or non-zero, and you only have a value if there's a non-zero coordinate. You can also talk about the encoding of the payload. It could be a fixed length payload, where every payload is always the same size, or maybe you'd have a variable length where you use one of the entropy type coding schemes like Huffman encoding to vary the size. So I also have a choice when I talk about explicit coordinate representations. So we already talked about coordinate payload lists, but we have choices there. We could have a form where the coordinate payload list is represented as a struct of arrays. So my entire fiber consists of 2 arrays, or a struct of 2 arrays, where I have the list of coordinates and the list of payloads or scalar values. Or I can do an array of structs form where the coordinates and the payloads are interleaved. And so I have an array, and each element of the array is a struct of 2 elements. I can also play with the payload encoding. I can make it explicit, where there is an immediate value or a pointer, reference to another value as the payload. There are also cases where the payload encoding itself can be implicit. If the offset to the coordinate in the array is actually the same as the offset to the payload of the payload in some other data structure, then you don't actually need to include any bits. You don't need to consume any bits for representing the payload. Okay, so what I'm going to do is I'm going to go through an example of a representation, and it's going to be an uncompressed, compressed representation of a rank 2 tensor. And here's my example. The top rank I am going to represent in an uncompressed fashion, and I'm going to represent the bottom rank, each of the fibers, in a compressed fashion. So how do I do that? So what I'm going to do is I'm going to represent for each coordinate in the top rank, and notice I have to have a representation for the coordinate which actually had no payload because it's uncompressed. And so what is the representation? The representation is an offset in the next rank to the fiber associated with this coordinate and its length. What was the length of the fiber? So this is a fiber that starts at position 0 in the rank and has a length of 2. This one it doesn't exist for reasons that will become obvious later. I'm going to also say it begins at offset 2 and has length 0. And then the third coordinate in this top rank has an offset in the next rank to its fiber of 2 and a length of 2. So the yellow values here are the positions in that uncompressed fiber, and the green boxes, which don't exist in memory, they're just the offsets. And the same with the green boxes down here. These are the offsets into the rank, which were used to find things. They don't appear in memory either. So what we see is because it was uncompressed, the position and the coordinate of the H rank are the same. And as I said, each of the values for the payload, because it's an implicit coordinate representation, are the position and length of the fiber in the next rank. And we notice here that now if we look at a fiber in the next rank, now its position and its coordinate are not the same. Those values are not going to match up. Okay, I just squeezed together the values in the top rank to show that those positions are all contiguous. And now I'm going to sort of squeeze together the values in the next rank. And as I said, I'm going to use a compressed representation. And so what I'm going to do is, before I do that, I'm going to note in this top rank that the first element of each pair is always the sum of the pair of elements in the previous cell. So 2 and 0 sums to 2, 2 and 0 sums to 2. And so obviously that information is redundant, and so I can actually avoid putting 2 elements in each cell and just put basically the start of each start and end of each fiber into this top rank, and I have to add this one extra cell so I can figure out the final length. Okay, now what I'm going to do, what I said before, which is I'm going to squeeze together the coordinate values in the next rank down, and so I have the fibers all contiguous here, 0, 2, 0, 2, and you can see how the references from the top rank say, here's your fiber at 2 of length 2, here's your, and it ends at the open interval ending in 2. Here's the next one, begins at location 2, ends at the open interval ending at 2, so it has 0 length. And then the last one begins at location 2 and ends at the open interval 4, so it shows the second fiber. So I'm sure that some of you immediately said, oh, so what you've created here is the compressed sparse row format. And that top rank is what in CSR would be called the segment array, and the second rank information is the coordinate array. but what I want, and then the information is in the value array. What I want to emphasize here is that this was a representational choice for the fiber tree abstraction, and we picked a particular representation for each of the fibers in each of the ranks, and we could end up with CSR. And like I said, that I could have many different representations. I could do array of structs or structs of arrays for the coordinate payload list. I could use a hash table. I could use a hash table per fiber where I look up by coordinate and get the payload. Or I could have a hash table per rank where I have a fiber ID and a coordinate, and the hash table would look up a payload for me. Or I could have a bit vector of non-zero coordinates and an uncompressed payload. So I could have all these choices, and then, inspired by a collaboration with Fred Kjolstad, who in a series of publications talked about the notion of representing tensors by picking representations for each of the ranks of the tensor. You can talk about like a little notation for the different representations for the fibers. So it could be uncompressed, run length encoded R, it could be coordinate payload list C, I could hash table per rank H sub R, hash table per fiber H sub F, or I could even do a tag union of any combination of the previous types or other types that you might come up with. Using this notation, you can actually think about there being a nice notation for succinctly describing a concrete representation. And so I'm going to say, well, what is CSR? CSR is a tensor where the top rank is uncompressed, the bottom rank is a coordinate payload list, and then I have a rank order of HW. Now, so I have that representation. Tensor UC of HW goes to CSR. I could do something where I reverse the order of the ranks. So now I have ranks W and H, where W is now the top rank, and the points, however, are the same. So let me do one that makes sense. So 2, 1 is H. So 1, 2, where I've reversed H and W, is H. So what is this? Reverse the ranks. I now have a representation which is still UC, but the order of the naming of the ranks is different. It's now WH instead of HW. And I'm sure that a number of you realize, well, that's the CSC representation. Another operation that I can do is I can merge ranks. So for efficiency, one might form a new representation where the data structure for 2 or more ranks are combined. And so if this is my original representation, and let's say that it was actually a coordinate payload list of HW, I can then smush it down into a single rank where the coordinates are now tuples of the coordinates from the original rank. So 0 and 1 becomes a tuple with its payload of A. 0, 3 is a tuple coordinate with a payload of C. 4, 2 is a smushing of these two coordinates from different ranks and becomes a tuple coordinate 4, 2, payload G, and in the end, 4, 3. Notice that I tried to color code this where yellow is coming from the top rank, white is coming from the lower rank, has a value of H. Could talk about this as a new representation where multiple ranks have been combined. So you could say something like, this is a tensor of C squared, where it's two ranks combined. And the reason I did that is because there are a variety of such combinations. A tensor of type C squared is a list of coordinate tuples and payloads. This is known as the COO representation. I could also have a combined hash table where I have hash tables from a tuple as a key to find out the payload of multiple ranks with one lookup. I can have a U squared. This is like a flattened array, and I can recover the original coordinates with modular arithmetic on the position of a lookup in that array. Or I could have a flattened run length encoded sequence, or I'm sort of combining two run length encoded levels into a single rank R squared. So what are the consequences of these variations? Well, one of the important consequences is the efficiency of traversals through the arrays, because that is affected by the representation that is chosen. And so the operations that are of particular interest are the one we've talked about before, which is get the payload by coordinate out of a fiber. So that was the kind of operation we used when we looked for a point in the fiber tree. Another one that is very common is that I want to be able to traverse a fiber getting consecutive coordinates. So I'd say fiber.getNext in a particular order. And fiber.next in particular is highly dependent on the representation, both the order of the ranks and the representation of each rank. So let's think about just traversal of CSR and CSC. And so if I have an original matrix which is represented in CSR format, there's a very natural traversal order. You want to traverse this by rows. You go down this row, go down this row, go down this row, go down this row. What we're going to do is we're going to call that a concordant traversal. It's a term that was coined by my colleague Michael Plauer. And going by row is the concordant traversal for CSR, whereas the concordant traversal for CSC is going by columns. And as we saw, what it's saying is if you go as sort of a depth first search through the fiber tree, that would be a concordant traversal, whereas a breadth first search, well, it's not even a breadth first search, but a non-depth first traversal of the tree would be concordant and would be much more expensive. Some examples of traversal efficiency. So if we think about the efficiency of get payload for uncompressed representation, it's a direct reference. It's order 1. It's very efficient. For run length encoding, however, if I want to find a particular coordinate by a particular payload by coordinate, it's going to involve a linear search down the tree because I have to go through all the run lengths. So it's going to be order n. If I have a hash table, might just be a few references and a little bit of compute. So more or less, it's going to be order 1. Coordinate payload list, searching for a particular coordinate in an ordered list is going to be could be done with a binary search. So it's going to be order log n. What about efficiency of get next? If I'm doing a concordant traversal, if I'm doing a concordant traversal for uncompressed, it's easy. It's just go to the next position. I have very good spatial locality. What about run length encoding? It's also sequential reference. So if I'm going to do concordant traversal using get next, run length encoding could be a good representation. Coordinate payload list is the same as uncompressed. I actually will just pick up consecutive non-zero elements of the fiber. What about efficiency of get next for discordant traversal? Essentially, it's going to be as good or bad as the cost of a get payload method. In previous section, we saw how we could use loop maps